So in 13.3, we are going to start taking the angles that we were working with yesterday and actually use some trig to start finding out some values of our trig functions. Couple of things to make the abstract a little more workable. Because I look up here and you're like, where is all this y and x and r and all this other stuff coming from? Basically, we're going to turn all of our angles into right triangles starting today. So by doing that, here's kind of a generalization that we can use. When we're talking about x's over here, we're going to be talking about the adjacent side of our triangle. And that'll even be true once we're given coordinate points. The y value is going to be the opposite side of our right triangle. And r is going to be our hypotenuse. So everything you know about the basic 6 trig functions is still going to be the same. It's just going to be the way we go about finding them. So like if you're looking at the trig functions in the box, it says sine of theta is y over r. It's opposite over hypotenuse, just like it's always been. Cosine is x over r, adjacent over hypotenuse, just like it's always been. Tangent's y over x, opposite over adjacent. Okay, so nothing's changing as far as the trig functions go. But what's going to change is how we can find these without maybe necessarily even having a triangle. So here's how this works. Since this is my x and my y values, of course, we would know that with any coordinate point. What this is actually telling me is what my adjacent and what my opposite is. So I could draw a triangle with this, but again, do I really want to? So with these, you're always going to be given the adjacent and the opposite. And what we're going to do is we're going to use the Pythagorean theorem to find the hypotenuse. Ooh, and I can tell some of you know your Pythagorean triples. This is good. If not, we can go old school. So if I know my triples, I'm going to know the hypotenuse here is 13. If not, you always can go old school, write it out, calculate this out, and get to your solution. So I'd have 169 as r squared. I'd take the square root and find out that r is 13, which again is going to be my hypotenuse. So, once I have all my information, just like I would with any right triangle, I can start whipping through these, just writing the fractions, not the decimals. So like here, sine would be opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. And then the inverse functions are just their reciprocals. And I'm ready to roll. So for any of these, and again, a lot of times you might be able to do some in your head. It's like 9, 16. Okay, so r is going to be 5, which is my hypotenuse. And then again, just burn your way through them. Opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent, and then just take their reciprocals to get their inverses. Now, it doesn't mean to say there aren't a couple of twists and turns that can occur here that can cause us issues if we're not careful. The one that seems to cause the biggest issue of all is the situation we get into in number 3. What happens if I come here and I have a quote-unquote side of my triangle that's negative, because we're not used to dealing with that? If you're going to go old school trying to figure out what your other side is, okay, figuring out your hypotenuse, you're going to want to make sure, especially that negative 15 ends up in parentheses, because we're not going to get a negative hypotenuse. They're always going to come out positive. And we're guaranteeing that by using the parentheses. So if I take 8 squared plus 15 squared and take its square root, I get a positive 17 out. So again, just make sure when you're doing these that you think about that. Oh yeah, the hypotenuse is going to be positive. Okay. Because then I can just start working my opposite over hypotenuse, my adjacent over hypotenuse, my opposite over adjacent, and then again, I'm just looking for the reciprocals on the other side. And if some of you want to take the reciprocal so far is to keep it on the 15 or on the 15 down here in the denominator, that's fine. As long as it's somewhere in the fraction, that'll be A-okay. So then, of course, got one other twist. What if it doesn't come out nice? What if it's not a Pythagorean triple? I sit here on this next one and I go 8, 12. Now, I don't remember that one being a Pythagorean triple because it isn't. I do my negative 8 squared and I do my 12 squared and I end up with 208. And here comes my issue. I could just leave it as that, but sometime, somewhere along the way, if this breaks down, and it does, I'm going to need to break it down. So again, when we talk breakdown, we're looking at two numbers that are going to divide in, but one of them needs to be a perfect square. The bigger, the better. What? 16. So 16 and 13 will get me to 208. Thank you. So my R, my hypotenuse is going to be 4 times the square root of 13. Hence lies the issue. Because now, when I go to work my trig functions, I'm going to have a radical issue, on some of them at least. So like here, for sine, I'd have 12 over 4 times the square root of 13. We'll come back to that in a minute. Cosine, we've got negative 8 over 4 square root of 13. We'll come back to that. Tangent, we have opposite over adjacent. We're even going to be coming back to that one too, because any type of reducing we can do, we're going to need to. But here's what I would do, and some of you may think this is strange at first, but that's okay. I would go ahead and write down my reciprocal fractions immediately. And I will explain why, and it will become a little more clear here momentarily. So right now, all 6 of my trig functions have one issue or another in reducing, as far as reducing goes. But 2 of them, sine and cosine, have the same problem, which is I can't have a radical in the denominator. So I have to rationalize it. So on those, reminder, rationalizing just means we're going to multiply the numerator and denominator by whatever that radical happens to be. But before you multiply across, notice the reducing we're going to be doing here. 12 over 4 is going to reduce to 3. So this is going to become 3, bless you, times the square root of 13 over, and again, that 4 is gone now because this became 3, and the radicals are just going to cancel there. So that's my simplified version of sine. 3 square root of 13 over 13. And it probably would have made it even easier on myself if I would have just reduced the fractional part right away. Because now I notice the only difference here is, now instead of being 3 over 1, it's going to be negative 2 over 1. So if I recognize that, I'd do negative 2 square root of 13 over 13. All of my other issues are just simple reduce a fraction. 12 over negative 8 reduces to negative 3 halves. They're both divisible by 4. which means this one will be the inverse of that, negative 2/3. Here, my only issue is to reduce the 4 over negative 8. And I could put the negative in front, keep it down here with the 2, doesn't matter. And 4 over 12 reduces to 1/3, or square root of 13 over 3. The reason I didn't rationalize my denominator right away is because if I would have, and then I'd have taken the inverse, I'd have had to rationalize it again. Who wants to do it twice? So I'm more of a fan of writing all 6 out first, then going back and trying to fix anything that I would need to. Otherwise, that's all we're really up to as far as those go. And those last 2 are just going to be the same types of situations. If you get a radical in the denominator, simplify it, is basically all that's going to say. Now, before you flip over, though, there's always got to be a special case to everything, of course. Sometimes, because we're going to get into talking here momentarily about reference angles and how those work, and I'm wondering if it would be smarter to do that first. Yes, it would. We will come back to quadrantal in a minute. This will give us a better reference anyway. So, reference angles. When I'm going to make these right triangles, it's going to make it easier on me if I have an angle that's smaller than I'm used to working with. So, we've seen before how quadrants work. Again, just going to work like a big C when I'm trying to figure this out. And depending on the quadrant that we end up in, that would make a difference on how we're going to find our reference angle. And I can do it algebraically with the formulas that are up here, or I can do it visually on a graph. So, if we look at it visually, like we're going to here at the start down below, it says sketch each angle, then find the reference angle. Now, a reference angle, if we want to simplify it, really is asking how far is it back to the closest x-axis. In other words, when I draw my graph, how far away am I from getting back to the x-axis? That's what a reference angle basically is. So when I go to draw an angle, and I can do it pretty quickly with 135, because anything, of course, under 180, I see on here right away. So here's my 135, and again, we'll just kind of slide that out of there. Okay, so there's my 135. But when we're asked for a reference angle, basically all you're being asked is, here's the next closest place on the x-axis. If I got all the way to there, that'd be 180 degrees. So how much of a difference is there between the two? 45. That's my reference angle. Now, if I didn't want to draw a picture, and in a case like this, I wouldn't really have to, understanding that 135 degrees would end up in quadrant 2, I could just use a basic algebra equation here and just say 180 minus the angle in question gets me my reference angle. And I'm done. So you're like, okay, let's test that theory out before we sketch the next angle. 200 degrees. Okay, so 90, 180. 200 degrees is going to be in the third quadrant somewhere. So if we're on quadrant 3, you take your angle measure minus 180. So 200 minus 180 is 20. Let's see if it works when we graph it. So I go to start graphing, and I go, okay, I get to 180. How many more do I need to get to 200? I need another 20. So I'd get my protractor lined up. And again, my last axis was the x-axis. That's why I'm lining up this way, and it's coming below. Why I'm having my protractor open down. So here's my extra 20. I get that drawn in. And just as I get that extra 20 drawn in, I go, oh, so basically, I was being asked, you know, how far is it? One thing about reference angles, they will never be negative. Even if you are going a negative direction, not going to be negative. We're just saying what's the difference between the two. So I could do it visually, I could do it with a formula, doesn't really matter. Now this one might get some of you thinking a little more, because it's in radians. Now, if you feel more comfortable looking at this as though it's a degree measure, you could. Because remember, pi is just equal to 180. So 5 times 180 would be 900. Divided by 3 tells me this is the equivalent of a 300 degree angle. But be careful. Your answer, since you started in radians, must finish in radians. If you go to degrees and leave it, which is what my regular class is finding out with me right now. So, if I was doing it strictly algebraically, 300 degrees would be in quadrant 4. Quadrant 4, when I'm in radians, would be 2 pi minus 5 pi over 3. But of course, I need a common denominator because they're not the same right now. So to get them the same, I would just multiply this 2 pi by the 3. Which would give me 6 pi over 3 minus 5 pi over 3, which is pi over 3. That keeps me in radians. But if you're not quite to that comfort level yet, that's okay. I can still draw my angle, figure it out in degrees, and then look back at it in a minute. So when I was drawing, if I got to 270, okay, I'm ending on the y-axis. So when I go to get my other 30 in here, I'll get lined up with the y-axis, heading out to the right. There's my 30. And here's the first one we have to be a little careful on. How far is it back to the closest x-axis? Not any axis. Back to x. If this is 300, getting back to x would get me to 360. It's 60 degrees. But if you do the degrees, you must convert back to radians. So if you went the degree route, make sure you multiply by pi over 180, and miraculously, you will end up with the same answer we got doing it mathematically before. Again, don't care which way you do it, but as long as it ends up in radians at the end. That's the thing that's killer. Got to do it that way. Okay? But that little chart at the top can be helpful as you're kind of getting used to this too. So okay, where's this drawing thing going to come in handy? Down here. This is something you are going to want to get yourself very familiar with because it will need to be entrenched into your brain. But there's an easy way to remember it. Basically what this is telling me is, depending on where my terminal side ends up, it's going to tell me whether my trig function is going to be positive or negative. So I start looking through and I'm like, hey, in this first quadrant, everything looks positive. In the second quadrant, it's just sine and cosecant. And the third is just tangent and cotangent. And the fourth one's cosine and secant. But like I said, there's an easier way to think about this. There's always a mnemonic. We seem to have them in math for everything. The way I like to remember it is something like, if you haven't heard this before, all students take calculus. If you can remember it, it goes quadrant by quadrant. All of my trig functions are positive in the first quadrant. Sine and its inverse are in the second. Tangent and its is in the third. Cosine and its inverse in the fourth. And that helps you remember, oh yeah, that makes this positive or negative. So when I'm looking for the value of the trig function and use right triangles, what that basically is telling you is, no, you can't just type sine of 150 in on your calculator, write down the decimal form of whatever, and say, I'm ready. Not going to work. Exact, use the triangles. Because we're going to get you used to, there will be a point when you get into trig where you'll have a no calculator quiz or test, and you'll have to be able to crank these out this way. So, just getting you ready. So here's how these guys work. We're going to do a few of them to get you guys going here. So, find the exact value. Okay, so sine of 150 degrees. I need to find my reference angle first. That's going to be the keys with these. So, what is my reference angle if my initial angle is 150? 30, because I know that 150 is going to be in quadrant 2. And if I'm in quadrant 2, let me come back down for a second here, it's going to be 180 minus my angle measure. So 180 minus 150 means my reference angle is 30 degrees. It's the reference angle I need to do all these problems. Because if I know my reference angle, I'm going to draw myself a right triangle here. So if I know my reference angle is 30, what's this other angle have to equal? 60. Something hopefully will start coming back to you here in a minute. 30, 60, 90 triangle. The sides of those have very specific ratios they take on. My short side, opposite my 30, always has a ratio value of 1. My long leg, opposite from the 60, is always the square root of 3. And my hypotenuse always has a value of 2. So once I have that set up, and I know this is the angle I'm referencing, what is the sine of that 30-degree angle in this triangle? 1 over 2, because it's opposite over hypotenuse. Now the only other thing I have to think about is the sine going to be positive or negative? Second quadrant, sine, it's positive. I'm done. If, this is a big if you want to double check to make sure you're right, at this point, ooh, I know what's going to happen to me. Mode, yeah, got to make sure I'm in degree. Okay. At this point, if I want to go to the calculator, it's 0.5, I know I'm right, that's fine. But it's not going to be one of those where you can go just to the calculator and go, oh yeah, and be finished. We're not quite to that level yet, because we're going to get to some of these, and you guys are going to be like, ooh. Okay. I'm going to skip number 11 for a minute, because that's a quadrantal. We're going to get to those special cases in a minute. Let's go to 12. Cotangent goes along hand in hand with tangent. 135 degrees. What quadrant are we going to be in? Second. So in the second quadrant, are tangent and cotangent positive or negative? They're negative, because in the second quadrant, only sine. So I know whatever answer I get is going to be negative. Mental note to myself. Like, okay. What's my reference angle going to be? 45. Because the closest x-axis is going to be when I get to 180. So 180 minus 135 means I have a 45-degree angle as my reference, which means I'm going to be working with a 45, 45, 90 triangle, which again has different ratios than the 30, 60, 90 does. On these, my legs, since they're going to be the same size, both have a ratio of 1. my hypotenuse is going to be the square root of 2. So I'm looking for the cotangent of my reference angle. If that gets you, just think about it this way for a minute. What would the tangent be? Opposite over adjacent. So it would be 1 over 1, which means it's just going to be adjacent over opposite, which is still 1 over 1. Which is basically 1. But and then I remember, oh wait, though, it's negative 1. So I'm going to get you thinking a little bit. Scary. Now, there's one more somewhat regular one I want to do before I go back to ones like 11 with the quadrantals here. What happens if they're in, radians already? Okay, remember, pi is 180. So 3 times 180 would be 540. Divided by 4, I believe is going to give me a negative 135-degree angle. Now remember, when you're graphing negatives, you're going clockwise. What quadrant am I going to end up in? Third. Nicely done. So we are going to be in quadrant 3. And in quadrant number 3, is sign going to be positive or negative? In quadrant 3, sign's going to be negative because in quadrant 3, only tangents. So we know our answer is going to be negative. So mental note. Next question. Our reference angle is going to be 45. Because again, if I did a negative 135, my closest axis is going to be at negative 180. So I just got to kind of keep these things in mind a little bit. So you're like, okay, so it's a 45, 45, 90, 1, 1, square root of 2. But I'm looking for the sine of my reference angle. So what's that going to get me? Okay, right, and I heard both things I would like to hear there. I heard somebody say 1 over the square root of 2, but again, I need to rationalize it, which is the square root of 2 over 2, but then I remember to put the negative on it because of the quadrant that I'm in. So that's always what I'm going to be looking for on these. Is it positive or negative? What's the reference angle? And then get it into this. What? Oh, go ahead. I'm sorry. Actually. Okay, now how do I want to explain this? If I were having to go back to a degree measure of something, I would have to go into radian. Because with these, the radians themselves, even like if I called this pi over 4 and pi over 4, I'd still be getting the same values for these. It won't change the actual answer that's going to be here. The time that you can get caught and stuck on a radian is if you're actually being asked what the angle itself is. Right now, we're just looking for exact values. Right. No, I'm glad you asked that because, yeah, that's the one time I can kind of look at it this way and then get away with it somewhat. But what happens if I'm given an angle measure that ends on an axis? 0, 90, 180, 270, something like this. Let's flip back over for just a second. Because here's the situations that we're going to get ourselves into. You're not going to have a triangle to work with, which is kind of strange because you're like, how am I going to get an exact value if I don't have a triangle? So here's how this works. You have a certain value at each of these coordinate points depending on if it's at 0, 90, 180, or down here at 270. And we've said before that our x and y values act the same way as adjacent and opposite do. So that's how we're going to treat these. So just as a reminder, x is still going to be adjacent, the y value within my coordinate point is still going to be the opposite, and r is still going to be the hypotenuse. You're like, okay, so what's really changing? Instead of me giving you a coordinate point with two numbers, one of your coordinates is going to be a variable, r. You're like, it's the hypotenuse then? No. Which is the tricky part. Here's how this is going to work. So since this is x and y in a regular coordinate, my x is going to be r. My y is going to be 0 in this first one. And we're going to label these, and then we're going to go back and we're going to do the hypotenuse, the hypotenusa. Yes. So then here, again with my x and y, my x is 0. My y is r. They just basically switched places. But when we start moving from there, now we start getting into negative values. And when we make it down to that third quadrant, we get here. And you're like, okay, so I've got x, I've got y, I've got my adjacent and opposite. How's the hypotenuse work? The exact same way. R is going to stay as itself. If you technically tried to do like a Pythagorean theorem or something on it, every single one of these you'd get r squared plus 0 equals whatever r squared is. You'd take the square root, you'd get r back. So for all of these, my hypotenuse is just going to continue to be r. So if I were asked to find any of my trig functions on one of these, let's say for 270, we were asked to find all 6 of your trig functions. Now, how would I do this? Well, I'll tell you what we would do. We'll get all these jotted down. And this way you'll have an example of how all of them would work, not just one of them. So I get this set, and I go, okay, sine is opposite over hypotenuse. Opposite over hypotenuse. Negative r divided by r would be -1. We're even going to test this out in the calculator in a minute, but I just want you to see how this would work if I didn't have one. Cosine is adjacent over hypotenuse. 0 over r would just be 0. If you divide 0 by something, you get 0. Tangent is opposite over adjacent. Uh-oh. Can't divide by 0. Tangent isn't defined at 270 degrees. And then I start going to my inverses. Now, it doesn't mean cotangent does not necessarily exist, because it does. But just because cosine exists doesn't mean secant has to. And then here, flipping those guys really doesn't change a whole lot. And we're ready to go. But again, if I wasn't sure, or if I wanted to double check, so I'm like, yeah, this seems kind of strange. Is this really true? I'm not sure. I could always take my theta value and just try, out of curiosity. Okay, -1. Cosine of 270. 0. Tangent of 270. Error. So I see, okay, yep, I've got this. This is going to work out okay for me. So, your task, as we always seem to do on all of these, is to deal with the bookwork on the back. Like I said, the homework check will be Wednesday, so you'll have a little bit of flex time when you get back. There will be one more thing we're going to do on Monday when we get back to do that. And you'll notice it's going to be the double dip because we're also going to have a quiz then. So